Hi everyone, and welcome to the recording of lectures 9 and 10 combined together. In the previous lecture, we introduced a couple of ways to have delays inside the tasks. The first one was an active delay, and we implemented it through a for loop that loops on a void, nothing at all, and that made us lose time when we are inside the CPU. And another way to delay in a more proper way was the use of task delay function call with the specified time in milliseconds when it comes to us as humans, converted to ticks when it comes to the operating system. And I've introduced and discussed with both the odd and even groups about the challenge of the proper delay, the first proper delay to implement periodic tasks. And we spent some time trying to find out another more efficient way to make sure that periodic tasks are implemented with the proper delay. And this is inter alia the topic of today's recording. Alright, so what I'm gonna introduce here is definitely recommended to create periodic tasks, and periodic tasks are tasks that are activated with a well-defined time or period of time. Alright, so in this system call here, we have something called task delay until, and we need to specify two attributes. The first attribute can be seen as a timestamp. So this is the time at which the task has left the block state, the last time that the task has left the block state. So you can see it as a timestamp. When did the task last leave the block state? And you can guess that the second attribute is definitely the time that we want our task to be delayed. All right. However, you should know that this timestamp is automatically updated, so it's not up to you. It's the real-time operating systems responsibility to take care of the automatic update of that particular timestamp. However, the very first time that you're gonna your task is gonna enter the state, the running state, it has never spent any time in the block state, hence you need to initialize it yourself. So inside the code of the body of your function, that is the body of the task, you should initialize it for the very first time. Fair enough? And this initial state or initial timestamp will definitely be the reference for your future coming out from the block state and getting back to the running state. So this is essential. So now we have a time reference and we know when we need to go back and run again, and we need to have the total time that we need to spend outside the running state, well, being blocked, and or any probable time that you'll be spending in the ready state, or extra time that you might be blocked, not active in. So this sets the frequency of the tasks. From now on, each and every time you're gonna implement a periodic task using any kind of real-time operating system, not only the FreeRTOS, it's systematically a never-ending loop, so a perpetual loop combined with a sleep time or block time, doesn't really matter, that should be specified and referenced to an initial value. This is systematically what you do whenever you're going to implement periodic tasks. All right. As I said, the operating system only understands ticks, so you need to, convert whatever time in milliseconds into ticks using a special system call. All right, so let's check an example here, and we're trying to implement a periodic task. So we are saying the body of task number 2. All right, so you can see that I'm trying to define the timestamp here called last wake up time, and I'm having some kind of string here that most probably I'm gonna spit out on the screen. And you can notice what I'm doing here is the first ever initial the first ever time I'm giving an initial value for my timestamp here. All right, so I'm using the system call task get tick count, and this is a reference, a time reference from the OS point of view for my very first initial value for my what do we call it, a timestamp. All right, so I said a periodic task is a perpetual loop, so this is my while true, while one, doesn't really matter. So this is an infinite loop, and I'm trying to print out something, and then this is where I call the delay, referencing with the reference to the timestamp that I have here, and that I have initialized here, and then the period of my task, which is 200 milliseconds, converted to ticks using this system call. Fair enough. And this is how we define periodic tasks. All right. Remember when I talked about the different parameters of tasks? So we decided back then to set 2 of them to null, and today I'm just gonna give you a quick explanation about the things that we set to null last time, and we're gonna try to use them as an example. Fair enough? Alright, so imagine that I'm creating some kind of string here and another string here. So you can notice, you can feel it, that the first one is going to be used by task number 1, let's say, and the second one will be used by the second task of the system. Fair enough. And for now, I've said that it is inside the main function that I'm going to create my tasks, right? Fair enough. So let's start with the first task that I want to create. And you can notice that I'm using the system called task create, fair enough, with the different attributes that I talked about previously. So we can have a pointer to the body of the tasks, or in a less sophisticated way, we can say that it's the name of the function that implements the task. This is a human name for the tasks, so we can debug, for instance. This is the size of the stack, and you already know whether if it's in bytes or words. And then the things that we set to null, we're going to use it here today, and another thing that we set to null, we're going to use it later today. And most importantly, because we're in the context of real time here, we have some kind of priorities. The closer to the 0, the lower the priority is. Alright, so here apparently we're using the text that we've defined here. Fair enough? We use the string or the pointer to a character, so it's a fancy way to say it's a string in C, right? Here. And yep, so this is the task I'm gonna use, the text that I'm gonna use inside of my task number 1, apparently. So I'm using it as a parameter. And I want to do the same thing with task number 2, so copy paste and change a couple of things. The things that I'm going to change is just the name, right? And same priority, good for me. And the last thing that I have here is the other task text that I defined here for the second task. Fair enough? You should notice something here. What do you notice? Correct. Apparently we're using the same function for both tasks. That's wonderful. This means that we don't need to copy paste if the two tasks are meant to do the same job. So basically we don't have to copy paste the function and make some changes in them. All you have to do is use something to make a difference. To differentiate between the tasks, and this is the role of the parameter that we have here. Fair enough? So same body, same function for the different tasks, and the only way to make the tasks do the same thing with different tasks, apparently we can feel that they are going to print messages just to debug or to understand the functionality of them. So basically both of them are meant to spit out messages on the screen. However, the first one will be spitting out my first task message, and the second one my second task message. Fair enough? Let's go and check the actual implementation of the function of the tasks now. So apparently this is the parameter that I'll be passing and using hence. And what you see here is whatever parameter I'm passing to the function whenever I'm creating the task will come here and inside something that I'm calling task name, and of course I want my task to be a perpetual one. So basically what I'm going to do is spit out whatever I'm passing through the parameter here. So parameter, task name, and task name, I'll be spinning it out. Fair enough? Same body for two different tasks, and the difference between the messages is here thanks to the parameter that I'm using here. That's it. Alright, so let's see an example here. So basically imagine that you've been recruited in, I don't know, at Tesla, and they are asking you to use a special Tesla real-time operating system, and someone is asking you to create two continuous tasks, so never-ending tasks, right, and one periodic task. So whoop, there's something that will pop in your mind saying that I remember Asan telling me during the embedded system course that whenever I want to create a periodic task, I need to do two things. First off is create a perpetual loop in my task and make it sleep in a way or another. Fair enough? Alright, so let's see the different characteristics or attributes. So the two continuum ones, they have the same priority here. Alright, and we're gonna use the task parameter, so apparently we're gonna use the same continuous print out string message. So basically both of them, they're gonna do the same thing. However, one task will probably print out its name or task number one, something like that, and the second one will print out a different message. So basically we're going to use the same body, same function with different texts. So most probably and most definitely we're going to use the task parameter. And this third task in my system is a periodic one with a priority of 2, and I'm going to make it sleep for 10 milliseconds total, including any time that I might be spending in the ready state or somewhere else. So I'm going to use the special delay that I've discovered today. Alright, so the continuous ones, same body, continuous tasks, and definitely we're going to use the parameter, so I'm going to put it inside the task name, getting it from here to here, inside here. Alright, continuous one, so perpetual loop, and just spit it out, and that's it. So the difference in the messages will happen throughout this parameter here. So we good. Let's see the body of the periodic tasks now. So I have a periodic task. Whoops. Alright, so I need the timestamp, remember. And I need to create my delay of 3. No, it's 10 milliseconds. Alright, so we need to change this into 10. It's not a problem for now. And this is the initial value that I need to do, right, before getting into my perpetual loop. So this is the initial value for my timestamp, and then perpetual loop. Inside it, all I have to do is spit out a message and then make a delay for, again, 10 milliseconds with a timestamp. right? So I only initialize it once, and then each and every time the task will be ready again, this will be done by the RTAS. The timestamp will be updated systematically and automatically by the RTAS. All right, and that's it. So let's see what we're gonna do in the main function here. So we need to create two different tasks for each of the continuous ones, and then we're gonna create three tasks. So 1, 2, 3, we got. All right, so two different continuous tasks using the same body, right? Two different human names, same stock size, doesn't really matter. The texts that are relative to each one, same period as specified in the spec requirement, and we're not using this one for now, so we're good to go. And the periodic one has a priority of 2, and this is so stupid because this one has no tasks. This should be null. So let's correct that. So this one is null. This is what happens when you do a copy paste. Alright, so we're good to go, and we're gonna kick off the scheduler. Alright, so let's observe what we're looking at here. Whoops. Periodic task has a priority of 2, the other ones they have a priority of 1, so this one will run first, and then it will go to sleep for 10 milliseconds. This will allow the other tasks to get to the CPU in a round robin way, in a time slice way, because they have the same priority until my periodic task is awake, so it will be back to the running state because it has a higher priority, so it will preempt the other tasks that are there. So this is an exact execution of what we wanted to happen in the specification requirements. Alrighty, so remember what I said, when we create tasks and we kick off the scheduler, there's a systematic idle task that is created by the OS, and actually you can create another task here. You can ask the OS to create another task for the for the timers. However, I'm not going to get into details about that one. It doesn't really matter. But what you need to understand is the idle task, and this is actually when you, if you're on your Windows home computer with a Windows operating system, of course, and you go ahead and press Control Alt Delete, and you go to the tasks manager. You're gonna see something called a system idle process or something like that, and this is actually the same idea. So you have an idle task that it's not a real task in the sense of doing something that is essential in a way or another, but it's a task that could handle statistics and tell you what is the percentage, what is the free CPU percentage that you have, for instance. Fair enough. So it's an indicator of, on how much you're occupying your CPU, for instance. Alright, so if we check this and check that, we can notice that we can guess that task number 2 has a higher priority here, so it started first, and then most probably it went to sleep. So this allowed task number 1, or this could be I wouldn't say it's a sleep thing, definitely. So because if it was a round robin thingy, we would seen the task number 2 here. So yeah, task number 1 is there, it executes, it goes to sleep, and yes, definitely they are periodic tasks because they wake up and then they execute again. And you can notice that they're always back into the system at the same specified period of time. So we got, and when those two are sleeping, right? So we have the idle task that is here up and running, and usually we can use it for non-real-time essentials. Yep, definitely. So can you guess the priority of the idle task? It's definitely the lowest one, which is 0. So we good. Alright, so yeah, task delay, blocked state, not able to run, not selected by the schedule, and this is an exact definition of a periodic task, so we good. there must be at least one task that is running, and this is the problem, the what do you call it, the idle task. Perfect. And most importantly, it has the priority 0, so it will never preempt any other task. Can we create some other task with the priority 0? User task? Yes, we always, as engineers, we always can. I mean, we have to really think about why would we do that. Alrighty. So what am I looking at here? Here you can see the last parameter that we set to null, so we're gonna try and understand it. And it's about the handle. So the last one that we used to set to null right after the priority is the task handle, and this is could be seen as an ID from the OS point of view, right? So we can use in order to do some stuff to get info about the task, etc., etc. And info could be anything from the what we called last year the PCB, remember? So it contains a lot of info. The most important info in the context of real time is definitely the priority. So for instance, you can use the system call task priority get in order using the handle of the task, so the last parameter, and we're gonna see an example of that, in order to do what? To do something about it. So maybe we can change it, and this is what we're gonna do. Alrighty. As I said earlier in some lectures, I don't remember which one, but I definitely said it, so I'm gonna re-say it one more time here. Some things needs to happen in the config.h, and this is the header file or the config file, right? So we can set some things in order to be able to use some functions. Fair enough. Alrighty. Let's see that. Whoops. So apparently there's a system call that will, again, that we need to configure the config.h file here in order to be able to use them. So a system call that will make us apparently use the handle and give it a new priority. So we're gonna use the handle of the task that we talked about in the previous slide, and then set a new, set or give it a new priority. Fair enough? So task handle and the new priority. Let's see an example, it'll be easier. Alright, so check this out. Task handle is null. This means that I'm creating some task handle that I'm gonna use in the task create, and of course, whoops, what am I doing here? So yeah, creating a task, and I'm not using the parameters. Good for me for now. Maybe I'm gonna use it for the second one. Yes, and this is what I'm doing here. So yeah, it makes sense. That's task number 2, right? So task number 2 handle that I've defined here doesn't really matter if I initialize it with null. Doesn't really matter, right? This is an initialization, and this is what we're gonna use here. So I'm giving this handle to task number 2. So whatever I'm gonna use the handle of task number 2, it would be this one. Fair enough. And that's it for my main. All I have to do is create my scheduler, and I'll be there. So let's go and check the bodies, so the functions of my created tasks here. Right, so for the first one, what I'm doing is, check this out. I'm creating a priority something. Oh, alright, so some variables that I'm gonna use to represent the priority. Good for me. And what I'm gonna oh, this is important. Let me, where's it? Erase that so it's clear. Alright, and let's go back to the laser pointer. So check this out. I'm using a function, a system call here called task priority get. Fair enough. So I'm gonna get the priority of whatever handle that I have here. Whoops, I'm using the null. I'm not using any handle, I'm using a null. This, whenever I use null, it means that I'm returning my own priority. So task priority got with the parameter here set to null, with a parameter set to null here, this will return my own priority. We good? So whatever my priority is, it will be in the in this variable. So I believe the priority of task number what do we call it? Task number 1 is 2, so we will have 2 here. Alright, so while 1 perpetual loop, I'm gonna spit out a message. Oh, fancy. I'm about to raise task number 2 priority. So how do I do that? Oh yeah, I remember. I just talked about something called set priority, so let's do that. Oh yeah, so yeah, priority set priority, same thingy. So I'm gonna set the priority. Hold on for a second. So I'm using task number 2 handle, so apparently I'm gonna change the priority of task number 2, and I'm gonna give it a priority of whatever I got here plus 1. So whatever I got here is 2, I'm gonna add 1 to it, so the new priority of task number 2 will be 3. Awesome. This means that at the very beginning, the task's number 2 priority was 1 and mine was 2. So this means because I have a perpetual loop, I will always run, and there's no way, Jose, for task number 2 to run. However, using what I did here, this means that task number 2 has a higher priority than mine, and a phenomenon will happen here, and this phenomenon is called preemption. So task number 2, because it has a higher priority than mine now, will kick me out. So yep, let's go and check the body of task number 2. So task number 2 can execute now. It executes. I'm gonna do the same thing. Alright, so I'm getting my own priority, and my own priority right now is 3. Remember, this is my first execution. And task number 1 just raised my priority to 3, and perpetual loop, spitting out a message, and I'm gonna lower my own priority. Makes sense? Alright, so now this means that this is my own priority, and I'm gonna take out 2 of it. So from 3 I'm gonna take out 2. This means that I'm back to 1. Oops, back to 1. This means task number 1 can now kick me out. I got preempted by task number 1, which has a priority of 2. And now my priority is back to 1, so yep, I'm out. And we're back to task number 1. We're gonna do the same thing. Higher the priority of task number 2, got preempted, come here. Lower the priority, got preempted, go there, etc. This is what we're seeing here. So task number 1 is running first, and yeah, I'm gonna raise the priority. Once I've risen the priority of task number 2, and hence we can see it running here, and then it drops its priority, and then we can see that it's preempted by task number 1, and we have an alternation between the different tasks. So it's a nice example. Alright, and we can surely guess that something is going on here, and what's going on here, you can have fun tracing, the uptime and downtime of the tasks here. By the way, will we ever see the idle task execute here? It's a big question. Let's try. You go ahead and try and think about it. Alright, so now we get to the interesting part of scheduling. So the question is, do you still remember the schematic here? Of course, these are the different layers of any computer, and because embedded systems are nothing but computers with some constraints, additional constraints, most probably timing constraints, right? So the question is, the answer to the question that is, why does real-time operating systems need to schedule? Well, the answer is to make sure that deadlines are respected. Fair enough. From the RTOS point of view, whatever application software here is a bunch of user tasks. Fair enough. And this is where you implement the different functionality of a system that you want to have. For instance, if you're implementing an embedded system that deals with autonomous cars, for instance, here you will have some task that will take care of the steering, the control of the motor, the speed of the motor, another task that might be taking care of the brakes, the signaling, the multimedia, etc., etc. Fair enough. And all of those, they need to respect some deadlines, and our task is here to make sure of that. The hardware layer, this could be anything from a microcontroller, as we've seen, such as the Atmega on Arduino, and you can have something else such as a soft processor here, such as Nice2 that you have seen in your tutorial. So this is fully coded in VHDL, and then it's uploaded onto in the VGA, and then you're gonna run some software on it, application software on it, right? Tuk tuk tuk, etc. Of course, it could be anything at all. And then, as an example here for this layer, we've seen the FreeRTOS here, and this here at GRC, and I personally work with the MicroCOS2, which is for avionics. Alright, and then this is you. This is whatever you're gonna implement. Alright, so the picture that you need to keep in mind is real-time constraints, railway example, the switching system. So this is a recurrent problem that we have in France. Is every single year there are problems with the trains because of the railway system. So it's something that happens all the time. So yeah, switching needs to happen on time, or else we can risk collisions, stuff like that. Flight control system example, you can think about the combustion engines, or even the landing gear, for instance. Everything needs to be done on time, so deadlines need to be respected. And another example, when we have timing constraints, it could be augmented reality, and we had a fun debate in class about the difference between augmented reality and virtual reality. And you can see here that an example of augmented reality is the Pokemon Go app that was fun some years ago. And my own personal experience with augmented reality is to have on the windshield of the car the information of the dashboard, so in the in the visual field of the driver. But you can see that even with systems that implement augmented reality, it's important to have the information that is projected in a way or another. It shouldn't be outdated. Alright, fair enough. So it all goes down to having a bunch of resources, and the most important resource in a system, in a computer system, is definitely the CPU. So we could be having one or more CPUs, but, most probably in embedded systems that you're gonna be dealing with, it will be a single CPU here, because with more CPUs the complexity will be higher, of course, naturally, and different other resources such as sensors, actuators, maybe memory, something like that. Alright, and the whole idea is how to assign whatever processors right we have, and the resources, in a way that all the tasks that we implemented, they're respecting their deadlines. Fair enough? Well, the whole idea of scheduling is to make sure that every task is respecting the deadline. Alright, and this is what we call the schedulability study of, or analysis of a system. Alright, why is that important? So basically here we have a bunch of tasks here, and you can see some of them, they have some resource, and all I have to do is to know how to place them and to check their dates, etc. I mean, to make sure that the deadlines are respected in a way or another. So we need to choose the order, etc. Right, so select or elect, respect select, respect. That's, it rhymes. And finally, why is that important? I mean, if we can study that before observing the system at runtime, before making everything run, this is perfect to give us some idea about how the system would behave. And this is what we call in the literature, I mean even in the industry, a way to improve determinism. So a deterministic system is a system that will behave in the same way provided the same context and the same set of inputs. So it will deliver the same set of outputs in the expected time, right? And there's a lot of investment in that, and we can never reach a 100% deterministic system in a pragmatic way. Alright, so this is something that you know from last year. We need to have some scheduling algorithm, right? And the scheduler, which is the module inside the kernel that will take care of the scheduling. We're gonna check the tasks that are ready and then order them in a way. So if we're using in FreeRTOS, we're using a scheduling algorithm, or actually even two scheduling algorithms. So yeah, do you remember those? So the first one, the most natural one, is the priority based one. Alright, so the task with the higher priority will go first, and in case of equal priority, we're gonna switch to a round robin, an RR, time slicing scheduler. Let's go. Okay, preemption, and we've talked about it so many times. So long story short, usually in real-time embedded systems, do you think that we have non-preemptive or preemptive scheduler? Usually it should be preemptive. All right, so yeah, preemption is kicking out a task with a lower priority to make space for a task with a higher priority. All right, fair enough. And this is what you need to know about it. All right. Yeah, that's quite interesting. So characteristics, real time and non-real time. What's the difference between the two? In one word, deadline. No deadline, no real time. That's it. All right, fair enough. A couple of definitions that are extremely useful for the for what's coming next. So let's imagine we have a real-time task called ji, right? So I could be anything, 0, 1, 2, 3, 4, whatever. So j, right? And we're gonna check its parameter. Parameter number 1, something called arrival time. Arrival time, also known ai. Well, I is the same I of j. So arrival time of task j I, whatever that is. Arrival to where? 3, 2, 1 to the ready state. Perfect. All right, something new here. We're gonna call it worst case execution time, denoted CI. Worst case execution time, also known as execution time, also known as, I don't know, what else can we call it? The needed time units for a task to complete its execution. Alright, so why do we call it worst case, by the way? Because in worst case scenario, this is the least amount of time that is needed by the task to complete its execution. Well, it's execution in the sense of, if it's a perpetual task, it will never complete its execution, but at least one iteration of it, right? So we're gonna work in iterations. Well, this is something we're gonna talk about later. Alright, so execution time, the minimum amount of time needed for a task to finish up its execution. Alright, something extremely important, real time, relative or absolute deadline, doesn't really matter. So the relative one is capital D, this one is small d, right? So absolute, small d. So absolute is wall clock time. This means that at any cost, before 12 o'clock, the lecture should be done. Let's say that. This is absolute. And then relative is relative to what? To when we got into the system. So it's relative to when the lecture has started. See? So if we started at 11 and the lecture should at any cost be over at before 12, this means that we have a relative deadline of 1 hour. if we started at 11:30, our relative deadline will change. Absolute one will never change. Good. Alright, start time, execution. When did we start executing? And finish time is the finish of our execution. We good. Mir gut. Alright, it's nicer to see it on a graph, of course. So here we can see what, let's see. Okay, so arrival time here, and we didn't get to execute straightforward, so we started our execution here, and this is the continuous non-interrupted needed time for a task to finish its execution. So this is worst case execution time, computation time, whatever you call it, whatever you want to call it, it's not problematic. And then here we have the finish time. Makes sense. Whoops, absolute deadline for sure, and relative deadline relative to the arrival time. So yeah, so what would be the mathematical formula relating this one to that one and that one? So this one would be something minus something, I would say. Alright, so the same blah blah that I said earlier. Anything new? Not at all. And of course, this one, the relative deadline is of course the absolute one with whatever flexibility, offered flexibility due to the arrival here. Let me think about something real quick. If I put my arrival here, yeah, so we need to be careful that whatever happens, we need to finish our execution before the absolute deadline, so we don't have a lot of flexibility here. Alright, start time, as I said, finish time, we're good. Oh yeah, something extremely interesting this year, extremely interesting, is the response time. So the response time is definitely not the response time of last year's course OS. The response time back then, it was the start of delivering of something. Here the response time is equivalent to the turnaround time. Please take like a red pen and write it somewhere. Response time in the context of real-time embedded systems is definitely the turnaround time. So from start, whenever we're done, when we got into the system until the very end of my execution. Fair enough? So here it will be when I got here all the way until I finished my execution. Fair enough? So yeah, is there a mathematical formula to relate the two here? So yeah, definitely it will be finish time minus arrival time. And it's correct. We good. Alright, there's a premise that I'm gonna follow, a hypothesis that I'm gonna follow in my lecture here, because it's the most relevant one and the least complex one. So we're gonna schedule nothing but periodic tasks. Alright, so forget about aperiodic tasks. Systematically, you're gonna think periodic tasks here. Hold on. So a periodic task, according to what I said, each and every time I'm going to create a periodic task, all I have to do is create a perpetual loop and then make my tasks sleep in a way or another. Sleep, like get blocked in a way or another. Alright? For a specified period of time, that's for sure. Alrighty, so check this out. These are the different hypotheses that I'm going to follow here. Alright, so every task has a period. Each and every time the task is back to the system, right? So it's ready again. Fair enough. It will be the same period, so the same body. I'm not changing the number of instructions. We good? So same execution time needed, same worst case execution time, same relative deadline. Doesn't really matter. I mean, relative deadline or absolute deadline, because the arrival time is fixed here, because it's a periodic one. Here, unless I say otherwise, you're gonna from now on consider that your deadline is always equal to your period, unless said otherwise. Fair enough? And the last thing, all the tasks are there I mean, if we have a bunch of periodic tasks here, they are already at a time 0. We good? Second premise, independent, no shared resources. We're gonna tackle that later on. And remember when we switch between different tasks, so what would happen? Who will take over for a small period of time, for a small time? Well, it will be the kernel, naturally, right? And more specifically, which module inside the kernel, the scheduler, right? So we're gonna consider the switching context, etc., etc. This will cost us nada, niet, nothing, right? So no overheads at all. So switching won't be visible when we're gonna trace our tasks because we consider it 0. Fair enough. This is the bunch of hypotheses that we're gonna take into consideration from now on. Alrighty, so yeah, periodic tasks, of course, naturally there are aperiodic tasks, and that's it. So we can see that here they are activated periodically, same period. We could define by period, unless told otherwise. Ti is equal to di. However, this is not a generic rule. This doesn't mean that di could never be different from ti. Of course, we can have a deadline that is shorter than ti. It happens sometimes. But unless told otherwise, you're going to consider that your deadline is defined by your period. Fair enough? And you can see the difference between aperiodic and aperiodic. So if you take a second to think about it, what's the difference between here and here? Yup. I don't see any period naturally, and most importantly, I'm not activated with the same tempo. So yeah, I'm activated sometime, but I don't know exactly when because there's no defined period, so it's irregular activation. Please take notes. I've mentioned it, so it would be only fair to mention it in the recording as well. There's a third type of tasks here. So we have the periodic, aperiodic, and there's something else that we call sporadic. It starts with an S, so sporadic tasks. S P O R A D I C. Sporadic tasks. And you must know of them just for the sake of knowing of them. So here you can notice that we have activation on a regular basis. Here I don't know when my next activation is because I have no defined deadline, so it's completely random. And those here, well, they have the worst or the best, depends how you look at it, of the two worlds here. So a sporadic task is activated within a defined period, but within that period we don't know exactly when. So it's random within a period, so it has a maximum time. So the next time at maximum it will be activated here, but I mean it could be anywhere in between the two here. Alright, so those are sporadic tasks. You just need to know of them, that's it. Alright, so we've seen a couple of scheduling algorithms last year, and I was interested in knowing your favorite ones in the lecture. So yeah, I don't know now recording, so you cannot answer me, unfortunately. However, yeah, we're gonna see two new ones, and special for the real-time paradigm. All right. Of course, real-time means that there should be some kind of priority, and the first one that we're going to talk about is a static priority. A static means that it's a fixed one. It doesn't change. It never changes in time. Fair enough. And the scheduling algorithm that we're going to tackle is called RM, so rate monotonic. And this is an old one, but it's a winning one, so it works perfectly. static, dynamic. Perfect. So yeah, we can either fix the priority or make it a changing priority. So here the priority of a task might, and I'm saying might, change throughout time, right? And the algo that we're going to talk about is called EDF. So take your time to guess what's E, what's D, and what's the F here. So D is definitely not dynamic. So it's earliest deadline first. Earliest deadline first. So the task with the earliest deadline will go first. Fair enough. Last thing that I want to talk about here is whenever we claim that the scheduling algorithm is an optimal one, this means that if a set of tasks, like a bunch of tasks, could be scheduled, right? So they are schedulable, right? The optimal one is able to do it. If in another way, if I rephrase it, if with an optimal scheduling algorithm I'm not able to schedule a bunch of tasks that are in my system, right? This means that they are no other algorithm will be able to schedule them, right? Fair enough. Yep. All right. So let's see an example here. So yeah, apparently rate monotonic is an optimal one for static priority. This means that if a bunch of tasks is schedulable, this means that rate monotonic can do it. And if rate monotonic cannot do it, no other scheduling algorithm can. That's a nice cheering motto. If Aram can make it, no one can. All right. Period priority. So priority is related to period. The smaller the period, the higher the priority. So small period, big priority. Good. So let's see. We have a task here, and we have two things about the task. So what do you remember what that is? Yep. Worst case execution time or computation time, whatever. Doesn't really matter. And this is the period of my task. So check this out. So we have 3 tasks here. This one has a period of 4, this one 5, and this one's 15. So which one has the highest priority? Static one. Yes. Priority number 1, priority number 2, and priority number 3. So highest priority, yeah, middle priority here, and low priority here. Be good. Alright, combination 1, 2, 3, it doesn't really matter. So 4, so I start here, right? Remember, no other info about the activation, so I'm going to assume that they are already at the same time. Arrival time, same arrival time. Second of all, no other info about the deadline, so I'm going to consider the deadline is equal to my period. We good? So this one period of 4, 0, 1, 2, 3, 4 here, 1, 2, 3, 4 here, 1, 2, 3, 4 here, etc. So see, you can see it's a periodic task. It goes back with the same period. What about that one? So this one is easier. So 5, 10, and 15. What about that one? 15. Oh, we're good. And next time it will be here. Alright, so which one will go first? Highest priority, which is the shorter period here. So this one, execution time 1. So I'm gonna go here. Who's ready next? Me and me. But I have a high priority than you, so I'm gonna go. So 2 execution time here. What about that one? No, I'm done, and I need to start my execution here. Whoop, careful. Someone is back into the system here, and it has a higher priority than I, so yep, preemption. I will execute here. I'm done. This one is back, higher priority, so this one will not continue. So 2 times here, and I won't be able to resume until here. See? Yep, and this one is back, so same thing. And you can imagine that what would happen. And filling in the voids. Alright, looks something like that. So you can have fun drawing it at home as well. Who can tell me, I mean, not a lecture. So If I wanted to check the response time of J3 here, J3, because I'm talking about the window from 0 to 15, so yeah, we good. So it's between arrival time and finish time. So I finished here, arrived here, so this is my, whoops, that's a weird looking arrow. Alright, this one's better. Alright, so you can notice this one. Response time for the first instance, because if you compare the response time of, if you want to check the response time of J2 here, you can notice that it arrived here and it was done here, so this is the first response time. However, we have another response time because remember, it was activated again at 5, and it's not the same response time. That's so crazy. You can see that. So for each instance of my task, I might have a different response time. Hence, we need to do a very complicated response time analysis later on. Alright? So you can notice that it's not only one response time, it's a bunch of responses. Well, alright, response times here. Alright, because we have different instances. Let's do that. Let's study the response time, and you're gonna do it. You're gonna do all the math in the tutorial. But what I need you is here is to understand what it is. What is it that you want to be doing in the tutorial? So task I 0, 1, 2, 3, whatever, right? It has at least the computational time, so this is its response for sure. And then this side here, let me use a pointer. All right, so computational time of my tasks. So task number 1, for instance, will have its computational time plus whatever, you know, delays or interference that is induced by higher priority tasks. So if I am the highest priority task, my response time will always be just my computational time. It makes sense, and this is what we've seen in J1 earlier, right? So whenever it's there, it will execute directly. So you know, arrival time, and start of the execution time are the same, and then it's done, right? However, the problem begins with the lower priority tasks, right? So whenever we have a lower priority task than the highest one, right, it will be computation time of that task plus whatever interference is induced by the highest priority task, and the second lowest priority task, whatever computation time plus whatever is induced by the higher priority tasks now, because there are more than one, right? And this is to reflect how the higher priority tasks are interfering with the response time of the lower ones. Fair enough? And this is the ceiling function, and this is the formula that scientists demonstrated in a juicy scientific paper in the literature. It could be fun. You can look for it on your favorite search engine and read it if you're curious, but we're gonna use it as it is. Fair enough? So ceiling function of the response time of my tasks in the previous instance over the period of the highest priority tasks multiplied by the computational time of the highest priority task, and we're gonna sum all the highest priority tasks. Fair enough? And you're gonna do a lot of exercise, a detailed exercise in the tutorial, so you can fully understand the mathematical reasoning behind it. Alright, yeah, so in order to know, and this is what we call the response time analysis for schedulability, to see if a set of tasks is scheduled or not. So we're gonna check the response time of some task number I with its deadline, and the response time should be lower or equal, worst case equal to the deadline. Why? Because if we're taking more time to respond, to finish our execution, and we're past the deadline, this means that we did not respect the deadline, hence our system will not work. Fair enough? It's a real-time system. We good? So at any cost, the response time should be lower than the deadline. Worst case scenario. worst case scenario equal to the deadline. Fair enough? If it's higher, this means that this task is not schedulable. Hence, this set of tasks is not schedulable. Only one task is not scheduled. This means that the whole system is not scheduled. I mean, the whole system is not correct. It's not doing what it's supposed to do. Right? The beauty of it, this is a necessary, of course, we need to respect the deadline, and sufficient condition. This means that if my response time respects the deadline, this means that my schedule, my system is schedulable. Right? And for your info, the response time analysis that I'm talking about, it works with any fixed priority algo. So basically, if you want to study if a set of tasks is schedulable using some fixed priority algo other than RM, fair enough, you can use the response time analysis. Alright? We do this whenever our deadline is not equal to our period. So this is the generic way to check if our tasks are schedulable or not. Fair enough? So deadline not equal to period. There's an easier way now. When the deadline is equal to period. Well, the schedulability analysis here, in case of a period that is equal, deadline is equal to the period, we can do something that we call the utilization bound test. Fair enough? So here we have a bunch of tasks like period and computation time, and there's this formula again that we're going to use as is. The U means that it's the computational time over the period of some task. Fair enough? And this is what we call the CPU utilization percentage, and usually it's a percentage. Fair enough? A ratio, a percentage. Alright, and we're gonna do it for all the tasks that are in the system. Fair enough? And if whatever we get here, by applying that and summing everything here, is lower than or equal to this side of the formula here, n being the number of tasks, right? So if we have 3 tasks, the n will be 3 here, right? If this is lower or equal to that, this means that the system is schedulable, and it's a sufficient condition. What is the difference between sufficient and necessary and just sufficient? Sufficient means that if we prove it, if this works, this means that we're good, right? But if it doesn't work, this doesn't mean that we're not good. This doesn't mean that the system is schedulable. In this case, what should we do? We're gonna go and do the response time analysis. Perfect. All right, something else. If the deadline is not equal to the period, we're not allowed to use this one. We need to go and do the complicated response time analysis, and you're gonna do it. All right, so let's check this out. So see, we're curious about that side of the equation, so the one with the n. You can notice that when we only have one task, we need to be lower or equal to 1. Right? Makes sense. If we have 2 tasks in the system, we need to, the C over the T with the sum of everything, it should be lower than that. Lower than that. What can you see here? Infinity, all we have to do is be lower than approximately 7% of the CPU. That's wonderful. That's wonderful. This means that the UB, right, with an theoretical infinite number of tasks, all I have to do is be lower than that. This means that all the time I'll be having 30% of my CPU that is free, which is wonderful. And I can use it, of course, for non-real-time tasks to do some statistics, stuff like that. We good? Right? And this is a visual way to see what I explained earlier. You can see the number of tasks getting higher and higher, and we can see that the utilization of the CPU will go lower with it. So the bounds is lower, and we're good. Of course, this is a screenshot from a paper. Of course, this has been demonstrated thoroughly in a paper, and we're gonna use it as it is. It's not the purpose of it to go into the details. Alright, now that we've covered the static priority, we're gonna go ahead and tackle the dynamic priority, and there is deadline first algorithm to be more specific. Here the whole idea is the earlier the deadline of the task is, the higher the priority of the task will be. Fair enough. And please note that on every tick, this is when the scheduler makes up its mind to change the priority of a task. So on every tick, we'll be able to change the priority of a task. EDF is not offered by FreeRTOS naturally, because we fix the priority, and then we can have some round robin. But I mean, we can in a way or another implement it as well as RM, because all we have to do is we can define periods in FreeRTOS, so we can fix the periods. Hence, we can fix the priorities according to the periods. So RM is covered. And earliest deadlines, this means that we'll be having to change the priority of the task, and there is a way to change the priorities when executing, but it would be a little bit more complicated than that. I mean, it's not that easy to do it, but it is possible, definitely. All right, fair enough. So on every tick, the scheduler will check the different deadlines of the task, and then it will pick up the one with the closest deadline. Alright, so same thing here. We're gonna consider that the deadline is the period, because we have no other instruction about it, and we have the computation time and the different things. So I think we're good. We can go ahead and try and do it. So period 4, 5 and 9. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. I think we're good. So here, same thing, no instruction. I'm going to consider that everyone was ready at the same time. So cycle 10 comes, and this one, it will be ready here for the first time. Back 9, yeah, makes sense, and back at 18. Wow, good. Alright, so let's see. We here, scheduler is asking which one has the earliest deadline, because deadline is equal to period, so we're gonna check. So we're here, so apparently it's this one. Alright, so this one will go first. It will finish executing here. Alright, so question now, which one will go next? This has a deadline of 5 here, so I have 1, 2, 3, 4 until the deadline, and here I have more than 4. So this one should go next. Oh, sorry about that. So remember, every tick I'm gonna ask myself, so what about now? Same thingy. This one is not back yet, so we're good. Alright, now it's done, of course, because both of them are done, so I can do that. One take, and then I'm gonna ask myself, this one is not back yet, this one is back, and its deadline is in 2, 3, 4 ticks, and that's 1, 2, 3, 4, 5 ticks, so this one should go first. See, this one is good, this one is back. Let's compare it with that one now. This one has 1, 2, 3, 4, 5, and that one has 1, 2, 3, 4. Oh, so you can notice that this one should go now. Alright, 1, 2, 3, 4, 1, 2, 3. It should continue, and you can notice that what's going on here. So this one will execute. This one is back. Should I continue? Let's see. I have 1, 2 until I'm done. And here I have 1, 2, 3, 4. No, I should continue. Yeah, if I'm not mistaken, this is it. Then you can continue it. Yes, that's it. Alright, I think we're good here. Alright, so one last thing, and this is the end of the lecture. If and only if, and this is the beauty of EDF, the U is, remember, utilization of the CPU, so this is a ratio. 1 means it's 100%. So if all the tasks that are changing dynamically, changing priorities dynamically, are under 100% of the occupation of the CPU, this means that my system is schedulable, right? This is the only formula we're gonna ever use for EDF. We good? Thanks for listening and watching, and hope to see you soon.